Hello dear students, in this lesson we are going to learn more advanced concepts in relational databases. We are going to talk about database normalization and denormalization. Believe me, this is really important lesson, and knowing the rules that I'm going to share with you in this lesson, you will be able to create scalable database architecture. And also this will help you a lot in your career. We are going to start the lesson from understanding of what data anomalies are. I'm going to explain what insertion, update, and deletion anomaly is. Knowing the problem, we'll learn how to avoid it. And after understanding of basics of dependency theory, we'll jump to our main topic today. I'm talking about normalization and normal forms that we are going to review with examples. And at the end of the lesson, we'll discuss what denormalization is. Let's start our lesson. And before we even jump to discussion of what normalization is, let's understand what problem we are going to address. Let me explain you what data anomalies are. Data anomalies are inconsistencies in the data stored in a database as a result of an operation such as update, insertion, and/or deletion. Such inconsistencies may arise when we have a particular record stored in multiple locations and not all of the copies are updated. Generally, a good relational database design must capture all of the necessary attributes and associations. The design should do this with a minimal amount of stored information and no redundant data. In database design, redundancy is generally undesirable because it causes problems maintaining consistency after updates. We are going to learn such term as normalization later today, but I already can say that normalization can help us to reduce data redundancy and minimize risks of data anomalies. But sometimes we want to add data redundancy on purpose. We need to do this carefully and with clear understanding of why we are doing this and what benefits we expect to get. Redundancy can sometimes lead to performance improvements. We are going to discuss how this may improve our performance when we will talk about denormalization. There are different anomalies. Let's review some of them. I'm going to show you different types of anomalies on example. Let's look at this example first. Imagine that we have a table with suppliers. We also store information about them, like address and products they produce. There is also information about quantity of each product and its price. Is that clear? What do you think about this table? Is it looks good to you? Well, we are going to review in detail what is wrong in such kind of tables. You already see huge data redundancy in this table. Also, I believe we can notice that relationships between key attribute and other data in tuple is not always logical. Let me show you in details what problems may be caused by this data redundancy. And the first anomaly that we are going to learn is insertion anomaly. Imagine that we need to add new supplier. We know its name, we know its address, but we don't know neither products that it produces nor prices for these products. We just started cooperation with them. Our company has been just registered. And what should I put in product, quantity, and price columns? I have to put empty or false data. In this case, I have to paste either null or zero in different columns. But is this correct? Why I obligated to come up with values for columns that I don't need to use at this moment? What if I just not aware about their products? Or why I have to update this tuple later with information about their products if I just could add new rows with the product? A lot of questions. Another type of anomaly is update anomaly. Imagine that we decided to update supplier name. Probably because of company reorganization, they decided to change their public name. And now we need to execute query to update all tuples where we used supplier's name. And we have really a lot of records where we need to update supplier's name. But what if we accidentally forgot that for some records during insertion we added LTD and for some not? What if accidentally there are different amount of space characters and some records still will be not updated? In this case, I am going to face update anomaly, because after update I will have inconsistent and not valid data. To not accidentally forget to update rows, it would be better if we could organize our database structure in the way when we have only one place where we store supplier's name. Then risk of facing update anomaly is minimal. Let's review deletion anomaly now. This type of anomaly may occur when we remove information, and together with it, we remove information that shouldn't be removed. For example, we stopped cooperation with one supplier, or we need just to remove information about delivery. And in case we remove information about delivery, we lose information about our supplier, and vice versa. All this information is important for our accounting department. We also might need to use this information to create different reports. What we should do in this case? It is a hard question to answer. Do you see what problems may be caused by data redundancy in our table? How to fix this? The best approach to create tables without anomalies is to ensure that the tables are normalized, and that's accomplished by understanding functional dependencies. Functional dependency ensures that all attributes in a table belong to that table. In other words, it will eliminate redundancies and anomalies. Let me show you the solution for our example, and what structure would help us to avoid data anomalies. Let's change our tables, and create two tables instead of one. We create supplier table, and also we create delivery table. In one table, we can store all information related to supplier, and in another table, we are going to store all information related to delivery. And we establish relationships between these two tables to avoid data duplication. For example, for each delivery, there is a specific supplier. Each supplier can have many deliveries. Each delivery is provided by one supplier. Is it clear? In case we want to add information about is it delivery or supplier, we are not obligated to add false information, or information that we don't have at this moment. No dummy values are needed during the insertion. This resolves our insertion anomaly. In case we want to update name of supplier or its address, we shouldn't do this in hundreds rows. We do this in one place, and reference to the supplier is still the same in delivery table. In case we want to remove information about delivery, but don't want to remove information about supplier, we just do so. We can delete tuples from delivery table without losing data from supplier table. Isn't this cool? That's why, to avoid these anomalies, you need to know what normalization is and its main rules. But before starting learn normal forms and normalization, we need to learn a little bit more theory. Because you need to know at least some key concepts from dependency theory in order you could understand normalization. Dependency theory is a subfield of database theory which studies implication and optimization problems related to logical constraints, commonly called dependencies, on databases. The best known class of such dependencies are functional dependencies, which forms the foundation of keys on database relations. And in this lesson we are going to review excerpts from dependency theory. Let's start. And as I already said, one of the main concepts in dependency theory is functional dependency. Functional dependency tells us that if we have two attributes x and y of some relationship, then y is functionally dependent on x. If in any moment of time each x value matches only one y value. X is said to functionally determine y. Functional dependency is a constraint between two sets of attributes in a relation from a database. For example, passport number and last name of the person, employee ID and his corporate email. we can say that there is a functional dependency between these attributes. The determination of functional dependencies is an important part of designing databases in the relational model and in database normalization and denormalization. This is important to understand because during the normalization of our tables, we'll investigate functional dependencies between attributes, and it is crucial to identify which attributes determine other ones. Now, let's understand some more details. Functional dependency between x and y may be called complete functional dependency in case y is determined by all subset of x. And again, I'm trying to simplify these concepts as much as I can, because in case I would tell you definition from the Wikipedia, it wouldn't bring more sense. For example, imagine that you have subset of attributes like place of dispatch, delivery destination, type of cargo, cargo weight. All these attributes determine price of delivery. Agreed? You can easily check this by removing any attribute from the subset and check whether the relationship is still valid. Because in case I remove cargo weight from subset of attributes, then the total price of delivery will be completely different. That's how easily I can check and ensure that there is complete functional dependency between set of attributes and another attribute. Does it make sense? And last but not the least important thing I'd like you to know about functional dependency is clear understanding of transitive dependency. Let me explain. Functional dependency x from y may be called transitive if there are dependencies between x and z and y, but there is no direct dependency between x and y. In this case, dependency will be called transitive. For example, there might be dependency between ID of employee and ID of office where this employee works, and there is another dependency between office ID and number of phone in that office. So, that means that dependency between ID of employee and his office phone number is transitive. Is it clear? Now, when we know what functional dependency is, we are good to proceed with learning of normalization and normal forms. Let's understand first, what is normalization? Database normalization is the process of structuring a database, usually a relational database, in accordance with series of so-called normal forms in order to reduce data redundancy and improve data integrity. It was first proposed by Edgar Code as a part of his relational model. Another definition of database normalization may sound like this. DB normalization is grouping and or distribution of attributes between different relationships to eliminate data anomalies during the operations with database, guaranteeing data integrity and consistency and optimization of DB. In the definition of normalization, we used such term as normal forms. What are normal forms? A normal form is a property of a relationship in a relational data model that describes it from the point of redundancy that can potentially lead to mistakes during the data insertion, reading, updating, or deletion. You already know about data anomalies, and you already saw examples. Based on this, I make a conclusion that you understand our motivation to learn normal forms. There are different normal forms. We can say that 3 of them are main ones. But we're also going to hold an overview of different normal forms in this lesson to help you understand this topic better. We are going to review normal forms from the least normalized to most normalized. In database normalization, unnormalized form, that is also may be referred as UNF, also known as normalized relation or non-first normal form. This is a database data model which does meet any of the conditions of database normalization defined by the relational model. Database systems which support unnormalized data is sometimes called non-relational or NoSQL databases. In the relational model, unnormalized relations can be considered as starting point for a process of normalization. It should not be confused with denormalization, where normalization is deliberately compromised for selected tables in a relational database. Normalization to first form requires the initial data to be viewed as relations. In database systems, relations are represented as tables. The relation view implies some constraints on the tables. No duplicate rows. Columns have unique names within the same table. Each column has data type which defines the allowed values in the column. All rows in table have the same set of columns. As you can see, most of the requirements are familiar to us and seems to be logical. But from the theoretical point of view, this is just starting point for our normalization, and a requirement that should be met before we start applying even first normal form. You can see example of a normalized form on the slide. This table represents a relation where transactions column is itself relation valued. This is valid relation but doesn't conform to first normal form, which doesn't allow nested relations. The table is therefore unnormalized. If this is clear, then let's move on. Let's proceed with learning of basic normal form, the first normal form. A relation is in first normal form if and only if no attribute domain has relations as elements, or more informally, that no table column can have tables as values. But this definition tells us that most relational databases are already in the first normal form by default, because it is impossible to have table value in a relational database. That's why I like another definition of the first normal form. Relationship is in first normal form if and only if each its attribute is atomic. What does it mean? Atomic attribute. This means that in your business domain and in business logic of application, there is no need to extract only specific part of the attribute to perform some operation with it. Let me explain you this on the example. Imagine that you have supplier table, and each supplier has its legal address. This address contains country, city, street, building, office number. But what if your application needs to perform operations with suppliers based on their country location? You need to be able to extract all suppliers from Russia, or all suppliers from India, or Ukraine, or USA. How you can do this with this data model? The only way for you to do this is to extract the whole address, then parse it inside the program and take only country value. That's why we can say that this table violates the first normal form. To make this table meet requirements of the first normal form, we need to introduce new columns in the table. Let's have separate columns for country, city, street, building, and office number. In this case, even when we need to extract suppliers from specific city, we can do this easily by using city attribute as a search parameter. Now we can say that our table meets requirements of the first normal form. Now it is time for the second normal form. A relation is in second normal form if it fulfills the following two requirements. It is in first normal form, and it doesn't have any non-prime attribute that is functionally dependent on any proper subset of any candidate key of the relation. A non-prime attribute of a relation is an attribute that is not part of any candidate key of the relation. In simple words, you have to store data in the table that relates only to the current entity, but not to another one. All attributes should depend on the whole primary key, especially if this is compound primary key. Attributes should have complete functional dependency with the whole columns in compound key, but not only on its part. This might sound complicated at the beginning, but in real life it is much simpler than you think. Let me show you this on example. I believe it will be easier to understand. Here is the table of items that we sell in our store. We have category, date, discount, and product name. There is compound primary key that consists from category and date. From this table, we can learn discounts that should be applied to goods from specific category at specific date. I believe that based on my explanation you already understood what is wrong here. Discount depends only on the product category and date. That's it. There is no direct dependency between discount and specific product. Product depends only on the part of the primary key. I mean only on the category. There is a dependency between discount for products from specific categories at a particular date. Does it make sense? Because in this case, we have data redundancy. So, what would be a solution here? The solution here is to make sure that complete functional dependency exists between all attributes and primary key. In our case, product has functional dependency with category, but not with category and date. That's why we create two tables. In the first table, we are going to have information about discount for category in particular date. And in the second table, we are going to store all products. This will allow us to have cleaner DB architecture. Let's learn cert normal form. A database relation is said to meet cert normal form standards if all the attributes are functionally dependent on solely the primary key without any transitive dependencies. The idea of the cert normal form is to not store data in tables that can be retrieved from other table attributes. Imagine that we have table of tutors at university. We have such columns: ID, last name, title, salary, department, and phone number. Is this table in the cert normal form? I don't think so. Let's try to visualize dependencies here. Salary depends on the title only. It doesn't depend on specific person. Specific tutor has its own title and works in concrete department, and they don't have personal work phone numbers. You can contact with them using phone in the department. That's why we can say that there are different transitive dependencies. For example, transitive dependency between concrete tutor, department where he or she works, and phone number. There is transitive dependency between phone number and tutor. Is that clear? To remove all transitive dependencies and make sure that all relations in the cert normal form, let's split this data between different tables. We need to create 3 tables to achieve this. Tutor table with last name, title, and department. Title table with title, name, and related salary. Department table with its name and phone. That's it. For some of my students, nothing is changed at the first glance. We just have more tables and relationships between different tables, rather than storing all data in one table in one place. And you need to understand me correct, because you can store everything in one table. This even has its own name, NoSQL. Just to let you know that this is also possible. But you would lose advantages that relational databases offer you. If you opt for relational databases, you need clearly understand what advantage you expect to get from it. That's why the rule of thumb is to follow normal forms. Code later realized that cert normal form did not eliminate all undesirable data anomalies and developed a stronger version to address this in 1974. Known as Boy's code normal form. To be honest, there are many other normal forms on top of these that we have just discussed, but in my opinion, these 3 are the most important ones. I am still going to make a quick overview of other normal forms, at least on the high level, in case you would be interested in more detailed explanation of all other normal forms, or you just have any question related to normal forms reviewed in this lesson, please ask me in comments below this video, and I will be happy to answer you. Elementary key normal form is a subtle enhancement on cert normal form. Thus, E, K, and F tables are in cert normal form by definition. This happens when there is more than one unique compound key and they overlap. Such cases can cause redundant information in the overlapping columns. A table is in elementary key normal form if and only if all its elementary functional dependencies begin at whole keys or end at elementary key attributes. Boy-Scott normal form is slightly stronger version of the third normal form. If a relational schema is in Boy-Scott normal form, then all redundancy based on functional dependency has been removed, although other types of redundancy may still exist. Fourth normal form is concerned with a more general type of dependency known as multivalued dependency. A table is in fourth normal form if and only if for every one of its non-trivial multivalued dependencies x, y, x is a superkey, that is, x is either a candidate key or a superset thereof. Essential tuple normal form for relations is a relational database where the constraints are given by functional dependencies and joint dependencies. It lies strictly between fourth normal form and fifth normal form. A relation schema is in essential tuple normal form if and only if it is in Boy-Scott normal form and some component of every explicitly declared joint dependency of the schema is a superkey. Fifth normal form, also known as project joint normal form, is a level of database normalization designed to reduce redundancy in relational databases recording multivalued facts by isolating semantically related multiple relationships. A table is said to be in fifth normal form if and only if every non-trivial joint dependency in that table is implied by the candidate keys. The main key normal form is a normal form used in database normalization which requires that the database contains no constraints other than domain constraints and key constraints. A domain constraint specifies the permissible values for a given attribute, while a key constraint specifies the attributes that uniquely identify a row in a given table. The domain key normal form is achieved when every constraint on the relation is a logical consequence of the definition of keys and domains, and enforcing key and domain restraints and conditions causes all constraints to be met. Thus, it avoids all non-temporal anomalies. Sixth normal form is intended to decompose relation variables to irreducible components. Though this may be relatively unimportant for non-temporal relation variables, it can be important when dealing with temporal variables or other intrivial data. A table is in sixth normal form if and only if it satisfies no non-trivial joint dependencies at all, whereas before, a joint dependency is trivial if and only if at least one of the projections involved is taken over the set of all attributes of the table concerned. As you see from high-level overview, it might be not so easy to understand the practical need and value of each of these normal forms. To know how to apply those, probably separate lesson is needed for each. But considering the fact that they are not so popular in comparing with the first three normal forms, probably I will not cover them in details in this lesson. I strongly recommend you to apply first three normal forms during the database architecture and during creation of each table. I might admit that knowing of all other normal forms by heart is not so critical. On the slide you can see comparative analysis. And the last but not the least thing that I wanted to discuss with you today is denormalization. Denormalization is a strategy used on a previously normalized database to increase performance. In computing, denormalization is the process of trying to improve the read performance of a database at the expense of losing some write performance by adding redundant copies of data or by grouping data. Denormalization differs from the unnormalized form in that denormalization benefits can only be fully realized on a data model that is otherwise normalized. So, how we can improve performance? Imagine that we have multiple tables. We have table with soccer clubs. We have table with soccer leagues. And we have table with match data. That should contain information about league, home team, and guest team. We also store a lot of other information about teams and matches. Now imagine that to extract much data for the whole day or week or month, we need to query 3 tables in database for each row. We may have thousands of matches, and not only in soccer. I simplified the original example a bit, but imagine that you have multiple sports, and you have teams in different sports, and much more leagues. This is literally crazy amount of data each day. Making join queries, finding the mappings in different tables may take some time. While it might be not so dramatic while querying few records, it is different when you query a lot of records. At the end of the day, we are receiving benefits by sorting entities in different tables without any duplication. But when you query thousands of rows and do join requests with different tables, this may take some time. And to save time by not querying other tables to get data you need, we add data redundancy on purpose. Do you understand now how better performance of reading operations is achieved? Imagine you need to read all matches data in normalized database, and you query in different tables. And in denormalized database, you request all data from one place. Do you understand the main idea of denormalization? But remember, this is something what should be done super carefully. You need to be sure what benefits you will get from denormalization, and it is recommended to be specific in order you could understand how many seconds you would win in performance after denormalization. I did this several times in my own projects, and I can say that this is technique that really worth your attention if you are going to use it smart. That's all what I wanted to share with you in this lesson. Let's recap what we have learned today. In this lesson we learned what data anomalies are. We have learned insertion, update, and deletion anomalies. Also, we reviewed the main concept in dependency theory. Now you know what complete and non-complete functional dependency is. After that, we learned what normalization is. On examples, we reviewed normal forms. And at the end of the lesson, I explained what denormalization is. That's all for this lesson. Thanks a lot for your attention. Have a great day and see you in the next lesson.